Good afternoon. I would like to thank the organizers for giving me the opportunity to present our results in this very nice conference. So during this talk, I will discuss the role of intermediate resonances in time-resolved two-photon transitions with particular reference to the rabbit technique. Now, resonances have been studied for a long time using synchrotron radiation. This is, for example, the original absorption spectrum of helium. Now, the asymmetric profiles corresponding to the resonant features were explained a long time ago by Fano in terms of the interference between a direct ionization path and an indirect path that passes through a transiently bound state. However, Fano's theory goes much beyond explaining the origin of these asymmetric profiles. It provides an expression for the phase of the resonant transition. However, the phase, which contains the temporal information of the resonant photoelectron wave packet, cannot be obtained with synchrotron experiments. So according to Fano, the resonant transition amplitude is composed of two terms, a resonant term which is intrinsic to the atom and one imparted by the field. Now, as a function of the detuning from the resonance, this factor describes a circle in the complex plane which passes through the origin and returns back to its original value. So the phase of the resonant transition amplitude starts at 0, grows up a little bit, and then at the point where the reduced energy equals minus q, so where this circle is 0, it falls down by pi and then goes back again to 0, and overall there is no net phase variation. So this phase information with synchrotrons is lost. Now, to retrieve this phase information, one can use this novel attosecond pump probe technique, such as Rabbit. So in Rabbit, one uses an attosecond pulse train in conjunction with a weak delayed IR probe to ionize the atom or molecule and record the spectrum as a function of the time delay. Now, the spectrum features harmonics corresponding to one-photon processes and sidebands due to the further exchange of one or more IR photons. Now, for example, sideband 2n can be populated from below by the absorption of harmonic 2n minus 1 and the absorption of an IR photon, or from above by the absorption of harmonic 2n plus 1 and the emission of an IR photon. Generally, paths 2 and 4 are negligible, and it is the interference between paths 1 and 3 that gives rise to oscillations of the sideband as a function of the time delay. Now, these oscillations have a beating frequency, which is the energy distance between these two states, and the phase of these oscillations incorporates the so-called atomic phase, which is precisely the phase of the two-photon transition amplitude. Now, how this atomic phase changes as a function of the energy tells us the group delay of the sideband photoelectron wave packet. In this way, for example, it was possible to determine the photoemission time delay between the 3s and 3p shells of argon. So let us use the Rabbit technique to extract the phase information of resonant transitions. So how does the Rabbit spectrum look when there is an intermediate resonance? Well, now, apart from the direct two-photon transition, one can excite a metastable state first. So from this metastable state, one can absorb an IR or emits an IR photon, or this metastable state can decay by autoionization to the continuum and then exchange an IR photon in a continuum-continuum transition, and so on. So Fano's theory treats the non-radiative coupling between the resonance and between the bound state and the continuum exactly and to all orders. Therefore, we should get accurate results if we plug in Fano's ansatz in the intermediate wave functions of the two-photon transition matrix element. And here is the result. So in principle, it coincides in form with the one-photon matrix element. Here, the reduced energy refers to the detuning of the harmonic from the resonance. However, Q now is complex. Now, the additional parameter zeta measures the radiative coupling between the resonance and the final continuum state as compared to the path in which the resonance decays first by autoionization to the continuum and then exchanges an IR photon. So what is the phase of this resonant two-photon transition matrix element? Now, if the resonance dominates the radiative coupling from the ground, and therefore Q is infinite, which is obviously the case for bound states, for example, then the two-photon transition matrix element as a function, as the harmonic crosses the resonance, forms a circle in the complex plane, and therefore the phase experiences a jump of pi. If Q is finite, however, then, and we're in the special case in which the resonance is not radiatively coupled to the final continuum, then Q is real, and the two-photon transition matrix element coincides with the one-photon matrix element. Finally, in the more general case where zeta is not zero, the two-photon transition matrix element splits into two circles, one for the upper sideband and one for the lower sideband of the resonant harmonic. Now, one of these circles goes around the origin, and therefore the phase excursion as we traverse the resonance is 2 pi. The other circle is shifted away from the origin, and the phase experiences a finite phase excursion with no net phase variation. So this is the result for very, very long pulses. However, in attosecond experiments, the pulse duration is often of the order of the lifetime of the resonance. Therefore, to get accurate predictions with the experiment, we must add up coherently all the chromatic components of the fields. We did so by folding the two-photon transition matrix element with the Fourier transforms of the XUV and the IR fields. As it turns out, if we use Gaussian pulses, this expression can be computed analytically, and the result is given in terms of the Faddeeva function. So the effects of this of the use of finite pulses is to contract the two circles I was talking about so that they both miss the origin, and therefore the phase excursion as we traverse the resonance gets greatly reduced. So we tested the predictions of this model with helium as a benchmark, since for it we have virtually exact ab initio solutions. So here is the ab initio rabbit trace for helium in the energy region below the n = 2 threshold, where a series of autoionizing states appear. So this would be the harmonics. You see that harmonic 41 contains the doubly excited state sp2+, and this would be the sidebands. So the effects of these doubly excited states should be visible in the neighboring sidebands. Now we look for these effects in the sidebands as compared to a non-resonantly populated sideband like 38, which will serve as a reference. So we zoom in the sidebands of interest. I remove the harmonics for clarity, and we see that the two resonantly populated sidebands, which are the two above, are shifted in opposite directions with respect to the non-resonantly populated sideband. Furthermore, this phase shift increases as a function of the time delay. Therefore, the presence of an intermediate resonance actually modulates the beating frequency itself. This is due to the fact that we are using pulses of 7 femtosecond duration, which is shorter than the lifetime of the resonance, and therefore a stationary regime is never achieved. Instead, the population of the resonance keeps growing with every attosecond pulse in the train, and consequently, the contribution of the resonance to the sideband increases as a function of the time delay. Now, in the bottom panel, I showed the comparison with the model, which is in very, very good agreement with the ab initio. So in particular, it treats very well the resonant effects and the finite pulse effects. So here I show the rabbit phase as a function of the detuning from the resonance for the upper and the lower sidebands. The gray line would be the solution of the ab initio, and the blue line would be the prediction of the model. We see that, as we commented earlier, the phase excursion is finite. There is no net phase variation, and both upper and lower sidebands are practically mirror images, one of the other. But another aspect peculiar to a resonant rabbit is the fact that the two-photon signal persists even when the pump and the probe pulses do not overlap. But more interesting, if we look at the upper sideband, we see that not only the signal persists, but a beating also persists. This is due to the fact that, as I commented earlier, harmonic 41 populates the sp2 plus doubly excited state, but for this frequency, the sp3 plus doubly excited state above is also populated by harmonic 43. Therefore, the phase of this beating encodes the phases of these two doubly excited states, and from it, we can, in principle, reconstruct the doubly excited state wave packet in a manner which would be alternative to those based in the holographic principle or in transit absorption spectroscopy. Now, finally, let me tell you about two recent experiments. So, we used the model to reproduce the rabbit trace for helium at 1,300 nanometers to reproduce the experimental conditions realized in the laboratory of Pascal Salier. So in their experiment, so this would be the harmonic resonant with the sp2 plus doubly excited state again. In their experiment, they measured the phase inside the sideband, which mirrors the phase profile that would have been obtained if we buried the detuning from the resonance. But it does so with a single rabbit experiment, only one frequency, and with much higher spectral resolution. So the blue points would be the experiment, and the red line would be the model's predictions, which is in very, very good agreement. And so the second experiment was done in the group of Anne Lullier in Lund regarding the photoionization of argon near the 3s4p autoionizing state. Again, the predictions of the model in this more complex system is, again, very, very good. Notice that in this case, in contrast to helium, there are two intermediate channels, one resonant and one non-resonant. The effects of the non-resonant channel is to shift the circle away from the origin so that the phase excursion gets reduced, and that is what is seen in the experiment, a smooth. So finally, I would like to tell a conclusion. So we have presented an analytical model which reproduces quantitatively resonant two-photon transitions in time-resolved experiments. In particular, the finite pulse formulation was instrumental in explaining two recent experiments and in formulating a novel means to reconstruct the metastable wave packet. And finally, the phase shift in resonant transitions does not generally undergo a pi jump, but a finite excursion. So I would like to thank my supervisors, Luca Argenti and Fernando Martin, our experimental collaborators in Paris and in Lund, and colleagues in Zurich and Australia for useful discussions. And thank you all very much for your attention.